Did you know the wind can act like a built-in storm compass? On large enough scales, there's a natural law that storm winds tend to follow. If you know which way the wind is blowing, you can often tell which direction the storm is. No radar, no computer models, and no weather app necessary. Stick around, because by the end of this video, you'll know the simple trick meteorologists have used for generations, and how you can use it the next time you step outside. But first, why does wind exist in the first place? The atmosphere is a fluid, and just like the water in your bathtub, any fluid naturally wants to flow from high pressure toward low pressure. Pressure is simply the amount of force exerted by a fluid over a given area, and it increases the deeper you go into the fluid because of the weight of the fluid above. When you first turn on the faucet in a bathtub, the higher pressure directly under the faucet is what pushes the water outward horizontally so it can spread evenly across the tub. In the atmosphere, air also wants to move from higher pressure toward lower pressure, which is why meteorologists track pressure systems so carefully. And this is why areas of high and low pressure are the main characters on weather maps, with highs labeled by a blue H and lows labeled by a red L. So simply put, air wants to move from high pressure to low pressure, and that pressure difference is what creates wind. But because Earth is rotating, as long as you're more than about 5 degrees of latitude away from the equator, and you're looking at large enough scales, say a few hundred miles, moving air tends to turn because of what's known as the Coriolis Effect. So air that tries to move from high pressure to low pressure ends up turning to the right in the Northern Hemisphere or to the left in the Southern Hemisphere, following the Coriolis rule. If you haven't seen my other video explaining Coriolis, be sure to check it out here. If we draw a simplified weather map with high pressure to the south and low pressure to the north, and with the black lines in between showing lines of constant pressure, also known as isobars, then place an air parcel at rest between them, here's what happens when we let it go. Initially, the only force it feels is the pressure gradient force, which pushes the air parcel from high pressure toward low pressure. There is no Coriolis force at first because the air parcel isn't moving yet. But the moment that air parcel starts to move, the Coriolis force kicks in and acts 90 degrees to the right of its motion, nudging it slightly to the right. As the air parcel speeds up, the Coriolis force increases too. And because it always acts exactly 90 degrees to the right of the motion of the air parcel, it continues to turn as it accelerates. Because this simplified map has straight, evenly spaced isobars, the pressure gradient does not change in between them. That means the pressure gradient force stays constant the entire time, while the growing Coriolis force keeps bending the air parcel's path. This process continues until the Coriolis force becomes equal and opposite to the pressure gradient force, with no unbalanced force along the path of the air parcel's motion or the wind. And from Newton's first law of motion, we know that objects in motion remain in motion at a constant speed and direction unless acted upon by an unbalanced external force. So if we assume there is no friction and that the pressure field is constant with no change in the pressure gradient force, this balance with the Coriolis force allows the wind to keep blowing indefinitely, perfectly parallel to the lines of constant pressure, or isobars. This is known as the geostrophic wind. The geostrophic wind is one of the most fundamental concepts in meteorology. It's the natural law that helps us figure out what winds are doing around storms, and it also allows us to estimate where storms are based on what the wind is doing. Geostrophic wind balance is what allows us to explain a rule called Buys Ballot Law, which states that in the Northern Hemisphere, when you stand with your back to the wind, lower pressure will be to your left and higher pressure will be to your right. So if you stick out your left arm, that points roughly toward the nearest low pressure area. And since most storms are low pressure systems, that means as long as you know what the prevailing winds are doing, you can make an educated guess about where your nearest storm is. Now, of course, real life is messier. When you add frictional effects, local geography, air blowing around trees and buildings, and other small-scale wind circulations, your position relative to the actual storm may not be exactly to your left. But as a general rule, this is a pretty good first-order estimate. And when you combine this rule with what you learned from my video about why storms spin, with air blowing clockwise around high-pressure systems and counterclockwise around low-pressure systems in the Northern Hemisphere, and with weather systems generally moving from west to east in the mid-latitudes, the next time you're out and about and notice a steady wind blowing from the south, chances are there's a low pressure coming toward you from the west. So you can expect stormier and rainier weather in the next day or two. Likewise, if you notice wind blowing from the north, chances are there's a high pressure system coming toward you from the west. So you can expect nicer and steadier weather in the next day or two. And so there you have it. Mother Nature follows laws, and there's a method to the madness, even in the way the wind blows. And now you know how to read the winds like a meteorologist long before there were computer models and apps. Be sure to subscribe for more simple breakdowns about how weather works, how to make sense of the untamed skies, and how to use that knowledge in your daily life. Keep looking up.